Hello. So today we're going to learn how to take the derivative of a product of two functions and a quotient of two functions. Right now our arsenal for taking derivatives, our bag of tricks, if you will, is kind of small because we just have that power rule. So today we're going to add two pretty big ones to our bag of tricks, and this week we'll probably also increase that, make that bag even bigger by adding, taking the derivatives of the trig functions and the exponential functions. Let's just jump in here. We're going to learn the product rule first, just because that's what you always learn first. I don't know why. Okay, so the product rule says this. We'll just start off if we're going to use this notation. It says if you have two functions times each other, multiplied together, that the derivative of a product of two functions is going to be the derivative of the first times the second plus the derivative of the second times the first. I do mine in this order. You will see some textbooks will put it like this. It's up to you. I do it this way because that's how I learned it 30 years ago when I was in Calculus 1. And I learned it exactly how I said it. And every time I do a product rule, I say it out loud. The derivative of the first times the second plus the derivative of the second times the first. So that's the product rule stated. Let's kind of look to see what it looks like in action. So just let's do a quick example of one. Let's say f of x is equal to 3 minus x squared times x squared plus x minus 1. Okay, so this problem, I mean, technically speaking, we wouldn't have to use the product rule to do this. I mean, if we were really into the distributive property, we could distribute this out or FOIL it if you wanted to expand all this out and just write a huge long polynomial and then take the derivative of each term one at a time. We could do that. But the product rule kind of saves us some work, because now I just look at these two functions and I think, okay, this one right here is the first and this one right here is the second. So when I do the product rule, I'm going to say that the derivative of this is the derivative of the first, which is negative 2x times the second plus the derivative of the second times the first. Okay, and that's it. We're done. At this point right here, I don't see any reason to do anything further with this. This is really just a practice, that we understand the rule. If you wanted to distribute this 2x and expand that and simplify that, well, you would have probably done that in the first place, and you would have never used the product rule. I kind of like it in this form because, I can see the derivative of the first, I can see the second, I can see the derivative of the second times the first. I can see everything right there packaged nicely, so leave it like that. Don't do extra algebra. Okay, so let me erase the board here, and then I'm going to give you a chain rule problem. Okay, I realize I said I'm going to give you a chain rule problem. That is not true. I meant to say I'm going to give you a quotient rule. We're going to learn the quotient rule next. I haven't had probably enough coffee today. It is like 7 o'clock in the morning right now. So let's talk the quotient rule. So the quotient rule is how we take the derivative of, you guessed it, a quotient of two functions. Sorry, I dropped my cap there. Let's change colors just for fun. A quotient of two functions. So let's say y is equal to, instead of f of x times g of x, we'll say f of x divided by g of x. Okay? And then I'm going to say the derivative of this. And notice I'm using this notation. And I'm just using this notation here instead of f prime. And because, well, for one, I'm not using f prime because f's part of the function that I've defined. But I'm not using the prime notation. I could call this y prime. I'm just using dy dx just to get you comfortable with using that. This notation is the notation that students tend to balk at, like they run away from. They kind of throw their hand. And so I want to try to just get you more comfortable with that. And the more I use it, the probably more comfortable you're going to get. I mean, what this means is the derivative of y with respect to x. So here we go. The quotient rule is this. There we go. Now, that looks like it's horrible to memorize, but it's really not. There's a little song I say in my head when I do this to help me remember this, and it's this: low, d high, minus, high, d low, over low squared. Okay? So if I think of f is high and low is g of x, so it's low, d high, minus high, d low, over low squared. And the proof of this rule is actually uses the product rule, but it also uses the chain rule, which we haven't learned yet. So maybe when we learn the chain rule, we'll go back and prove why the quotient rule works. But you can see these are going to get messy. I mean, there's a lot of, there's fractions involved and a lot of multiplying and terms in the numerator. These could get algebraically messy, but we're not going to beat ourselves up simplifying these. Okay, let's do an example of the quotient rule real quick, so you can see that. How about f of x equals 3x plus 1 over 2x minus 4. Okay? So, a pretty simple little function, right? So what's the derivative of this function? Okay? Now we know that this function that we started with, by the way, is not continuous at x equals 2, because that denominator would be 0 at x equals 2. This function has vertical asymptote at x equals 2. So since it's not continuous at x equals 2, then we know that it's not differentiable at x equals 2. So its derivative is not going to be defined at x equals 2 either. And you'll see when we get to, when we finish writing out the derivative, you'll see, oh, it's not differentiable at x equals 2. Here we go. So, quotient rule, low, sometimes you can go low, d high. So we look at the numerator and you say, okay, what's the derivative of the numerator? Derivative of 3x plus 1? 3. Minus, and oh my gosh, don't forget that minus. It's not plus, it's minus, okay? Minus high d low. What's the derivative of the denominator? 2. Over low squared. Okay? So technically speaking, friends, this is the answer. This is it right here. This is the derivative. We can simplify this, and I'm going to simplify this a little bit just to kind of show you some key things that we can often forget. But this is correct. This is the answer. From here on, it's algebra. But back to what I said a second ago, hey, look at that. See the derivative? It's not defined at x equals 2 either. So that stuff that we talked about last week actually is true. Huh, that's funny. So if I simplify this numerator, and we're not going to necessarily do this every time, but I want to show you something. We'll distribute this 3. So 3 times 2x is 6x. 3 times negative 4 is negative 12. And then minus, I'm going to backwards distribute this 2. Now this minus is going to have to distribute through the whole thing. And this is why I wanted to show you this. So this will be 3 times 2, or 3x times 2 is 6x. And 2 times 1 is 2. And now, if we simplify one step further, (6x minus 6x is 0. Negative 12 minus 2 is negative 14. Okay? So I wanted to kind of go through that with you just so you could see that this minus sign here is so crucial that if you needed to simplify it, if I were to ask you to simplify one, and I might ask you to simplify one like this, because it's not terrible, but you've got to remember to distribute that negative through, okay? Because it's minus high d low, the whole thing, that whole product. Okay? So this is the quotient rule. Now I'm going to erase the board and we'll do a couple of examples that mix up the quotient and product rules. And then that'll probably be enough to turn you loose. Okay, here we go. So got an example here. This is a function that we're just calling g. And I'm going to say find the derivative of this thing. Find the derivative function. Right now we're just finding the derivative. We're not technically using the derivative for anything. We could plug in points and find an equation of a tangent line for this function, but right now we're just finding the derivative. So now we have to kind of decide, this is where, now that you get some more rules under your belt and some more tools to use, you have to sort of talk through things. Like when you look at this problem, you kind of have to have a conversation with yourself and say, okay, well, what do I see here? Well, I see two things being multiplied together, right? I see a radical. I see a cube. Both of those are pretty easy to take the derivative of individually. So I think in this case, I just have, this is just a straight up product rule. So let's do it. And again, every time I use the product rule, people, every time, I've been doing this for 30 years. God, that's a long time. I guess it's not quite 30 years, but close enough. But I've been doing this a long time, and still to this day, when I do the product rule, I say out loud, the derivative of the first times the second plus the derivative of the second times the first. I say it out loud every time, and so should you. So here we go. Now, maybe before I write this, or before I take the derivative, it might be helpful for you to think of this as 1 plus x to the negative x to the 1/2. And then hopefully you can subtract 1 from 1/2 appropriately, unlike me, who last week in a video subtracted 1 from 5/2 and somehow got 4/2. Whoops. I think Megan, it was Megan that pointed that out to me. So, yeah, sorry about that. It would be nice if you were sitting in here and you could catch my arithmetic mistakes. But anyway, here we go. So the got to move this down a little bit just so it doesn't get in the way. The derivative of the first. So I'm going to take the derivative of 1 plus x to the 1/2. Well, the derivative of 1 is 0. The derivative of x to the 1/2 is 1/2 x to the negative 1/2 times the second, x cubed minus 1, plus the derivative of the second, 3x squared, and the derivative of 1 is 0, times the first. Done. That's the derivative. Okay? If we wanted to rewrite this, we could. We could try to simplify this. But honestly, the only thing that's going to make this look pretty is just putting it in radical form. You could distribute this and clean that up, but I'm not sure that I mean, we're not gaining anything there. I mean, we're just proving, hey, look at what I can do. Who cares? I'd rather you understand calculus than be able to do all that algebra. Okay, let's do another example. I think I got enough room here. How about this one? H of x is equal to 1 plus x times 1 plus x squared to the negative 1 power. Okay? It's good coffee. All right, so what are we going to do here? Well,
good morning, everyone. Today is Monday.
I'm going to pause so you don't have to listen to this. Okay, so sorry about that. That was Mr. Alexander. We actually did the pledge. I could have just left that unpaused and you could have done the pledge with me because you guys probably haven't done the Pledge of Allegiance in probably 6 months. But anyway, so here we go. I'm looking at this function that I called h, and I've got the product of two things, right? And so your first inkling is like, oh, got this product rule, yes. I got a product rule here. So I think, okay, well, and you can do this with the product rule, but maybe you can't just yet. Because I've got this, I can take the derivative of that pretty easy. But this function right here, I don't think that you've learned yet, well, I know you haven't, because I'm your teacher, I don't think that we've learned how to take the derivative of some function to a power. Now, we've learned how to just take the derivative of a power, like x squared, but I don't know how to take the derivative of this function to a power. And I know that no one in this, watching this video, would even dream of sending that exponent down in each one of those, because that's illegal. So we don't really know how to take the derivative of this second term yet. But we will. So now I think we're going to have to rewrite this. So let's rewrite it like this. Are those two equivalent? And you should be like, yeah, they are. Duh. So now I can say, oh, this is just straight up unleaded quotient rule. So here we go. So again, a couple things before we get going on this quotient rule. Make sure, you guys, that you're paying very much a lot of attention to your equal sign and where you put things are equal and where you don't. Like this right here, I wrote h of x equals, and then I wrote h of x equals. Now I'm going to say h prime of x equals. Okay? It's not equal to this. Don't be just putting equal signs for things that aren't equal. All right? And then now we're going to execute the quotient rule. So we say lo 1 plus x squared. I kind of try to sound like Mr. Byer. Lo. Lo, d high, derivative of the numerator. What's the derivative of 1 plus x? Just 1. Minus high, d low. What's the derivative of 1 plus x squared? It's 2x. Good. And then over low squared. And that's the answer. Okay? I think typically what I'm going to do on a lot of these quotient rule problems is have you simplify the numerator only. So we can just bust that out real quick. So that's going to be 1 plus x squared minus 2x minus 2x squared over 1 plus x squared squared. And then a little combining like terms. 1 plus x squared minus 2x squared is minus x squared minus 2x plus 1 over 1 plus x squared squared. Okay? So there's another example. Let's do one more. I'm going to pause. Okay, this is our next example. So I've got f of x is 1 plus x minus 3x squared radical x all over x. Okay? So Now we got to think about how are we going to find the derivative of this sucker. Again, it always helps that we should always look to rewrite the function before we use any derivative rules. We could do the quotient rule here, right? I mean, we could take the derivative of the top and the derivative of the bottom. Ain't no thing. But we could probably simplify this process or this problem significantly if we just busted this up into an equivalent expression. Say like 1 over x plus x over x minus 3x squared radical x over x. Okay? We undistributed this. We factored out the 1 over x. We wrote this as 3 separate fractions. Okay? Whatever you want to call it, that's what we did. And now I'm going to do one more rewriting. I'm going to call that x to the negative 1. I'm going to call that 1. And then I'm going to call this x squared and x simplified to just 3x radical x. And then I'll do one more rewriting. Because maybe we don't know the derivative of x radical x off the top of our heads. So maybe we have to think of that as x to the 3/2. At some point, my guess is as many of you are going to just be able to take the derivative of this in your head. Okay? But if you have to write it as x to the 3/2 right now, ain't no thing. All right, so let's do it. Let's take the derivative. Notice, I think we're going to get away with not using the product or the quotient rule in this problem. Derivative of x to the negative 1 is negative x to the negative 2. The derivative of 1. What's the derivative of 1? 0. The derivative of any constant is 0, right? So that's going to be plus 0, and then minus 3/2 times 3 is 9/2 x to the, and then 3/2 minus 1. I said you're probably going to get really good at subtracting 1 from fractions, and then I stunk it up in that last one. But 3/2 minus 1 is 1/2, because 3/2 minus 2/2 is 1/2. And, I mean, that's the answer, right? I mean, I guess we could just rewrite this if we wanted to make it look pretty. But, I mean, I think it looks okay like this. I mean, this is just making it look a little bit prettier. No big deal. So there's an example of one that we thought maybe we had to use the quotient rule, but if we did a little bit of algebra, we actually made the problem simpler. You know, I think it would have looked a lot messier had we used the quotient rule. It wouldn't have been incorrect. In fact, let's just do it real fast. Why not? I got some space here, so I'm going to say, okay, using the quotient rule, it would be low, d high. Okay, now before I do d high, I'm going to at least think of this right here, just because I only have a little bit of space left over here. I'm going to think of this right here as x to the 5/2. So d high is going to be low, d high, 0 plus 1 minus 15/2 x to the 5/2 minus 1 is 3/2. It is today. So that's low, d high, minus high. Uh-oh, I'm going to run out of room. 1 plus x minus 3x radical x all over, that's high d low. D low is 1. All over low squared. Okay? So I don't know if you can see that, but I'll rewrite it again. Just lower so you can see it. Low, d high, minus high, d low, over low squared. Okay? So that is the quotient rule. We did it right. And this is equivalent to that. I mean, which one would you rather do? I mean, if so, sometimes a little algebra on the front end pays off on the back end. Like, you don't have, I mean, if we didn't do all that algebra on the front end, now we have this hot mess, which is just, I mean, this is just ugly, okay? So that's the product and the quotient rule. I'm going to give you some problems for you guys to play with, and it's going to be in the same section. In fact, I believe one of the problems I gave you last assignment, I think it's 3.3, but one of the problems actually involved using the product rule. That was my mistake. So, yeah, have fun with the product and the quotient rule.